Yeah, so we can start in a couple of minutes. What, Mark, Sai, Helen, maybe? Is that fine? No. And maybe people have moved.
Okay, and we still have some echo issues.
Yeah, I think.
Still have.
Yes. Okay. Apart from the presenter, everyone should mute and close the videos once she starts presenting. Apart from the presenter, everyone should mute and close the videos once she starts presenting.
Just a question, should I keep my video on while presenting?
You can continue using your video.
Okay, it's I mean, as you wish, whether the video is supposed to go with the slides.
It seems to work.
Yes.
YouTube is working now. So we can start. YouTube is working now. We can start. Helen, your feed is visible there. YouTube. Helen, your feed is visible there.
Sorry?
YouTube.
Yeah, Helen, you're on YouTube, so probably you can start opening the session.
So we're live streaming?
Yes.
Great. Okay. So welcome to WICED 2020, everyone, and let Hyen and Vineet open our workshop. So everyone in the Zoom room, please mute your microphones and also make sure that you're using headphones so that we don't have feedback on the computer.
Okay, Sai, you would like to go first? Maybe, yeah. So we'll just take.
Can everybody hear me?
Yes.
I heard echoing.
All the participants, please. Microphones. Please mute your microphones.
Yeah, please
it's a request.
Mute YouTube. Everything except for Zoom. Is it better? Yes, I think so. Okay, shall we start?
Yeah.
Hi, hello everyone. My name is Hyen Li. I'm a professor in the Computer Science Department of National Chengchi University in Taiwan. And it is my great pleasure. Is it okay? Is the sound okay? You can try to turn down the volume. Could you say again?
I think there's some feedback from the computer.
Okay.
Do you have headphones?
Not for now. I can look for one. But probably I can go first.
Yeah, so yeah, I'll go quickly. Will not take a lot of time. Lucille is waiting. So I think I'm assistant professor at IIIT Hyderabad in India. You know, me and Sai be chairing this session, and since it's a feat that we have pulled off in this workshop in a challenging situation like this. You know, some point we are not even sure what will happen. You know, a while ago. So I think thanks to a lot of hard work from Mark and Helen. You know, especially Helen has put a lot of work. You know, so really thanks to her. Thanks to the reviewers to putting things in time and so on. I'll probably thanks more people in the closing note, but so the highlight of the workshop is there's a good mix of academics and industry people. So it's really exciting to see a lot of interest from the industry people, and I think we have an exciting program ahead today. And we'll start with a keynote with Lucille, and with that, I think I'll pass it on to Helen to take it forward, maybe, or we wait for Sai for a minute if he can fetch a headphone and come, and if he wants to add anything. So, I think, yeah. So we'll just wait a minute for Sai, and then Helen, over to you to introduce Lucille. Okay.
So while we wait for Taiyan, so before we enter our program, we will have a live Q&A on WICED. And so after each presentation, we will have a live session where we can take questions from participants inside the Zoom room, as well as questions from the YouTube and Discord. So if you are in the Zoom room with us and you would like to contribute to a question, please raise your hand during the Q&A session, and we will call on you and you can pose your question. So, Taiyan, would you like to say something?
Yes, although I haven't heard what Vinay has said. But again, I would like to welcome you all to the NICE International Conference on Intelligent Cinematography and Editing this year. And I think I would like to thanks to the support by the Eurographics team to make this virtual conference possible and smooth. I hope so. And I hope that despite the distance that we are trying to keep, all of us can enjoy the presentation today, probably in a more free form. And we all know that this workshop has historically been strong connected to computer graphics, animation, and other topics like in interactive and automated camera control and visualization. And I think this year we have seen more work on VR 360 streaming contents for live events, dynamic and autonomous camera, and or automated editing, which I think is more interesting, and also means that the virtual cinematography technologies are becoming more practical and physical, which I think is all what all of us would like to see. And again, I'm very grateful to co-chair the program with Minette this year, and I hope that you will all enjoy the talk. Okay, that's all I have, and hope everyone has a great day today.
Yeah, so welcome everyone again, and over to you, Helen. Okay. Thank you, Sayan. Yeah, so.
Yes.
Thank you. So without further delay, let's begin our program today. And it's a great pleasure and honor to introduce our first speaker and keynote of our workshop, Lucille Cizatelli. So Lucille is an associate professor with habilitation in the University of Côte d'Azur and a member of the CNRS I3S laboratory. And her innovative work focuses on using attention-driven techniques for creating efficient and personalized experiences in virtual reality, placing her work at the intersection of multimedia networking, human-computer interactions, and virtual reality. And the significance of this work is outlined in her numerous publications in selected venues, in the projects and recognitions she has received, notably a junior chair in the prestigious Institut Universitaire de France and Excellence in Dash Award, just to name a few. And WICED has always celebrated interdisciplinary research, and Lucille's keynote today continues this spirit by introducing us to the realm of computer networking. So Lucille, thanks again for being with us today, and we can't wait any longer to hear your talk. If you can unmute your microphone in Zoom.
Others can also please close your videos apart from Lucille. I think it'll save some bandwidth. Maybe just close your video.
Okay, sorry, I didn't have a proper handle on Zoom while sharing my screen, so I'm trying to share again. Can you hear me well? It's fine?
Yes, we can hear you.
Okay, so let me share again. Is everything fine now?
Yes, we can see your slides.
Okay, perfect. All right, so, well, thanks so much, Helen, for the very nice introduction. And thanks to all the chairs for the invitation. It's a great honor to be the first keynote speaker in this 2020 edition of WICED. So, so I'm Lucille Sassatelli. I am an associate professor at Université Côte d'Azur, and I am affiliated with the I3S laboratory, which is the computer science laboratory joint between the university and CNRS. And I also hold a junior chair with the Institut Universitaire de France. So the title of my talk today is When Virtual Reality Editing Meets Network Streaming. And as the title suggests, I come from the networking community. So let me first introduce myself and my colleagues as we make for a quite interdisciplinary workforce. So I come from networking. So I worked for quite some years on mobile networks, wireless networks, and then I moved on to multimedia networking back in 2015. So I specifically focused on the networking problems raised by massive video streaming. And for a bit more than 3 years now, I've been focusing specifically on immersive content, and as I will detail, on 360-degree video streaming. So on these networking aspects, I work with my colleague, Ramon Aparicio, and as I'm going to present, I work quite a lot with user-centric approaches to multimedia networking, and specifically with human-computer interaction. So on this topic, I collaborate with my colleague, Marco Winkler, who is the head of the HCI group at I3S. We also work quite a lot with, and more with machine learning approaches, of course. So I collaborate with my colleague, Frédéric Precioso, on that. And we've been co-supervising a number of students, and specifically some students who have been really key in the works that I'm going to talk about. So Miguel Romero, our doctoral student, our PhD student, who will present right next, and some former master students, so Savino Dambla, Giuseppe Samela, and others. So I won't speak about projects, but I just want to mention one new European project in which we are involved, which is AI for Media. So AI for Media is one of the 4 European networks of excellence centers in AI. This one is targeted at media, and I'm the PI for Université Côte d'Azur. Okay, so here is the outline of my talk. So I will first start by presenting the problem of 360-degree video streaming and how is that an interdisciplinary problem. I will then review quite quickly most important works in attention driving techniques for 360-degree videos, as this is at the core of my presentation and our questions that I'm going to present today. And I will then present the new interdisciplinary levers that we have introduced to improve VR streaming and that go to the user side. Specifically, I will present dynamic film editing or snap changes and virtual walls that we have designed. And finally, I will give conclusions and discuss the interdisciplinarity of the problem, taking some perspective on it. All right, so let me start with the general presentation then. So in this talk, I'm going to focus on immersive contents and specifically on 360-degree videos. So 360-degree videos are videos that are meant to be watched in a headset, isolating the user from her environment and immersing her or him completely into a new world. So, of course, this type of content hold great potential for a number of applications. Specifically, it can lead to new types of journalism, of fiction, of storytelling content. And well, VR, so virtual reality, has been dubbed the empathy machine by director Chris Milk due to the unprecedented feeling of closeness, of proximity to the characters that it can bring, and that can be either embodied or perceived, and that can allow some changes in perceptions of specific problems like discrimination, for example. And another aspect which is quite promising application of VR is remote education. So to give access to high quality education for remote populations in rural areas in rich or poor countries. So this is all very, very promising and very exciting. But the problem is that the development of immersive contents is persistently hindered by three major types of issues. So the first issue that is faced is the headset technology. So we know that the headset technology is not mature. It often leads to eye strain, fatigue, cyber sickness, and it still has a long way to go. The other type of issues is the design and production that still face a number of questions, in particular in terms of understanding what is the attentional process during a VR experience and how it connects to the autonomous nervous system, to the vestibular system, as the entire body is involved. And in this talk, I'll be talking about attention driving techniques for compelling contents. And the last but not least issue which is faced for development of immersive content is the distribution. So unlike regular videos, 2D videos, the streaming of high quality VR experiences is still an unsolved challenge. And this is what I'm going to talk about today, how to stream 360-degree videos over the internet for the best experience. So let me now detail what's the problem here. So it's difficult to stream 360-degree videos because they require a much higher data rate than regular videos. So the data rate can be 2 orders of magnitudes as that of regular videos for 2 main reasons. The first one is that, well, the content is wider, so it corresponds to can correspond to basically 6 videos packed together. So 1 in the front, 1 in the back, 2 on the sides, 1 beneath and 1 above. And since the video is meant to be watched an inch away from the eyes, the resolution must be much higher. So this is the major problem. So one simple approach that I've been investigated in the multimedia community for some years now is to say, okay, at each point in time, the user does not have access to the entire sphere, but only to a restricted angular sector, which corresponds to the field of view. So let's tile the sphere, the video, into pieces encoded in different qualities, and send high quality only the portion of the sphere that the user has access to each point in time, and low quality the rest of the sphere. And this way, we have what we call a field of view based quality adaptation technique. So this is the idea, and this principle is a priori very nice. The problem, of course, is that when we consider now that the server and the client are distant, and we have to go through a shared internet, through a shared network like the internet, that can suffer from congestion in particular, as we know quite well now, latency can increase. So if the latency increases, then that poses a problem, because that means that the server is going to need to know in advance what's going to be the motion of the user in order for this field of view based quality adaptation strategy to work. And this is, of course, difficult. So in regular internet connections, the latency is ranges from from tens of milliseconds, few hundreds of milliseconds, and can go up to a few seconds in times of congestion. But the thing is that if we additionally have at the client side what we call a playback buffer, then this latency, this end-to-end delay between the production and the consumption in the headset is systematically high. And that means that, of course, the latency, the end-to-end delay is higher. But the thing is that the playback buffer is a key element in modern video streaming because they allow to absorb for the latency and the bandwidth variations of the network. So the latency is therefore systematically high in case we allow such buffer. So here everything worked nice in this animation, but as I said, in case we have congestion, then the playback buffer is absolutely crucial because it's going to prevent playback interruptions. So here, for example, in this case, we have a congestion that slows down the arrival of the different segments. And in case we do not have any playback buffer, then we would have a playback interruption. And we know that playback interruptions are very detrimental for the quality of experience of the user. So here, for example, we have, if we consider that each piece here corresponds to 1 second of video, so each square here corresponds to a segment of 1 second, then if the playback buffer can hold 3 segments, then that means that the latency, the end-to-end latency, is at least 3 seconds. Okay, so now what's the problem with that is that, of course, if the latency increases, then that means that the prediction problem that the server has to solve to know what's going to be the future user's motion is much harder. So if the prediction is wrong, that means that it's not the area which is sent high quality is not the area which is going to happen into the user's field of view in the end. Then 2 possibilities here. Either, the user is going to face low quality areas. So this is a problem because the quality of experience is going to decrease. And in case the prediction is wrong and we have time, so we have enough bandwidth to have late replacements. So if we get close to the playback deadline and we realize that some tiles that have been downloaded in low quality are going to happen into the field of view, then we might trigger some replacements. So download them again into high quality. So that means that in both cases, here, the very specific characteristic of streaming 360-degree videos, we have visual quality and the consumed data rate that are getting dependent on the human motion. And here, this is what gives very solid ground for interdisciplinary approaches, as I'm going to detail now. Okay, so we have this problem. Visual quality and consumed data rate get dependent on human motion. So now the question that we face when trying to devise some 360-degree streaming algorithms is to how to handle the user's freedom. So the first general strategy, which has been considered in the networking community, in the multimedia networking community for some years now, is quite simple, quite straightforward, yet very difficult to achieve. So it's basically to predict the motion. And we've seen that if we do that over quite long prediction horizons, so just a few seconds, a few more than hundreds of milliseconds, then the problem gets very difficult. And what we have done is that in our first work, is that we have introduced a different yet complementary approach, which is that instead of trying only to predict the user's motion, we are going to try to partly control the motion. And the idea here is to limit the randomness of the motion and exploit the a priori knowledge of pieces of the motion in the streaming algorithms. So the question we have been trying to answer is how can we design some attention-based, some new attention-based levers that can be instrumented into 360-degree streaming algorithms in order to improve the user's experience. And of course, I'm going to talk here about filmmaking and specifically film editing, designing some specific types of editing cuts to achieve such a goal. Okay, so now that the problem has been introduced, let me review a bit the attention driving techniques. So here the idea is that the attention driving techniques can be really key in improving the way we stream 360-degree video over the internet. So there's been a number of works, of course, in attention driving questions. So I'm going to review them a little bit here. So I first categorize them into 4 classes. So the first 3 classes here corresponds to techniques which are meant to suggest to try to lead the user to new field of use, while the last class here corresponds to really enforcing some field of view change that is partly independent of the user's motion or the user's will. So in terms of guidance techniques, we can distinguish between diegetic and non-diegetic visual cues, so either incorporated in the story plot or not, and of course, cuts for scene transitions. So regarding first guidance with diegetic visual cues. So here I'm going to put a few references. Of course, I'm not targeting, I'm not trying to be exhaustive, just giving some example works at the bottom of the slides and detailing a few in the core of the slides. So here, an example of diegetic visual cues is the work of Knorr and others. So they have explored the efficacy of different directional cues like sound, environment, actions, which have actually been set and manipulated by a director, which has configured them so as to plan a certain trajectory of the field of view of the user that the user is supposed to take thanks to these cues. And then they've compared the actually planned trajectory of field of views with the actual trajectories that have been made by the users, this way assessing the efficacy of the different cues. So in terms of non-diegetic visual cues, there's been also a number of works. So for example, in 4, Daniel and others investigated different ways to basically impact the display of the field of view in order to lead the user outside the current field of view. So they tried fade to black effects. They tried some desaturation effects, some kind of blurring effects, and some kind of wave deformation effects. And they've concluded on the difficulty of leading the user outside the current field of view. In another work, Lin and others readily displayed thumbnails of external field of views superimposed onto the current field of views and indicating in which direction the user has to move in order to reach them. And in another work, Gregoric and others took another approach where they designed a subtle driving techniques, which is meant to remain unconscious to the users. And this technique corresponds to some flashing dots, which whose shape, intensity, and flashing frequency varies based on the distance between the targeted field of view and the current field of view of the user. So these were kind of examples. And of course, the other class is cuts for scene transition in cinematic VR. So in VR, in 360-degree content, the editing does not only correspond to arranging over time the different scenes, but it also requires to choose the relative angle between two successive scenes, and choosing this relative angle is going to control where the user is going to land in a new scene, given where they were looking at in the previous scene. So this is very important. So there's been very important work in studying the effects of cuts in cinematic VR. Of course, the work of Serrano and others who have investigated whether legacy movie editing techniques can also be used, can transpose into VR. And they've identified that regular continuity editing techniques can work in VR. And specifically, what was very interesting is that they've investigated the impact of having angular misalignment between the region of interest between two different successive scenes, the impact on the user's behavior. And specifically, they could identify that the time for a user to reposition onto a region of interest when entering a new scene varies exponentially with the angle difference between the regions of interest between the successive scenes. So that was very interesting in terms of understanding the impact of the editing on the user's behavior. And another interesting work has been that of Lille Lund, and others that have investigated the impact of cuts in VR onto the level of disorientation of the user. And very interestingly, they have shown that high frequency of cuts, high frequency of changes of scenes can be very well supported by the users, provided that attention is correctly guided at the point of the cut. And so that was some kind of guidance techniques. And now let me talk about the techniques to direct changes in field of view. So the first set of techniques consists in having the change of field of view still initiated by the user, but where the system is going to assist the user in moving by moving in some way which is not entirely controlled by the user motion. So an example here is the work of Yu and others. So they proposed some kind of rotating bookshelf in order to reposition a user at the entrance of a navigable room in the virtual environment in case the position of this room does not correspond to the navigable space in the physical environment. So in case we have some mismatch to reconcile both in the user's perception. In this work in 11, Sargunam and others have addressed the problem of seated users. That was also one of our motivations in our work. And what they did is that in order to facilitate rotation without bringing too much to the neck, they amplify the head rotation of seated users compared to what they actually turn. So the angular displacement in the virtual environment is wider than the angular displacement in the physical environment. And another work which was also very connected to what we have found is that of Farmani and others. So they've investigated some discrete viewpoint techniques in order to lower the level of cyber sickness of the users. And specifically, they proposed some type of rotation snapping to reduce cyber sickness. So here the idea is that when the user starts to rotate, in case the angular speed of the head exceeds 25 degrees per second, Then they go into a fast fading transition, and then they have a viewpoint snapping by increments of 22 degrees. So that means that when the user turns their head too fast, then there's going to be a fade to black transition, and it's going to come back to the regular image every 22 degrees until the user stops. So that would be like the user closes their eyes and then open them again, and then closes again, and then open them again until they stabilize onto another field of view. So that was all techniques that were initiated by the user, even though the displacement ends up being not exactly that of the physical displacement of the user. And the last types of techniques is when we have field of view changes which are not initiated by the user. So in particular, for example, we have Rarimi and others that proposed automated transitions initiated by the system. So basically, the user is toggled from one point of view to another. But the disadvantage of these techniques is that the repositioning is progressive. That means that the participants experience vection, and that increases their level of sickness. So all this work were very in the same mindset as what we did next. And let me now go to the presentation of our different levers that we've designed. But first, let me just properly state the general research approach that we've been taking in all these activities. So the research objective that we have is to improve the quality of experience of 360-degree video streaming with new adaptation levers which are based on attention driving techniques. So the idea is to devise some new types of attention driving techniques that can be instrumented into a streaming algorithm. So the rationale for that is the following. We considered that given the discrepancy between the data rates which are required by immersive contents and the data rates which are actually available on the networks, given that the streaming decisions must be made based on the user's motion, and given the radically new type of experience of VR environments, contrary to regular videos, we consider that and we believe that it is important to introduce and to design a wider set of levers, not only compression, so not only variations of visual quality, as I presented first, that would enable, so these new levers that would enable to modulate the immersive content in order to help streaming this content. So the approach I'm going to present now, well, the specific lever I'm going to present now, has been our first strongly interdisciplinary approach that built on networking, human-computer interaction, and filmmaking. And specifically what we did is that we designed editing cuts which are meant to consume less bandwidth while maintaining the level of user experience while streaming 360-degree videos. So what we have introduced specifically is what we call snap changes. So this is the way we control partly the field of view of the user. So a snap change consists in repositioning the user in front of a predetermined field of view in a snap. That means from one frame to the next. And this way, there is no vection which is experienced, and the vestibular system is mostly not involved. So let me show you an example of such a snap change here. At 6 seconds, you'll see that on the video. So hope it plays well. So here the snap change in front of the region of interest is happening. And then the user is repositioned in front of the region of interest, and we may have some lower motion. So here, what's the idea? Of course, the user is going to undergo this repositioning. But we posit that if the repositioning is made in front of a meaningful region of interest that might have been decided beforehand by the director, then this repositioning might go unnoticed. And also because these type of snap changes are types of intrascene cuts of changes of shot, and that corresponds somehow to fast cutting, to which we are so much used. And on the other side also, such kind of manipulation corresponds to take some freedom off of the user. And doing so, what we expect is that this is going to limit the amount of randomness of the motion, and this is going to translate into bandwidth saving. So in order to, to test our hypothesis, of course, we have designed a whole set of processes. So we've made an Android app, which is a 3-degree video streaming player. It is based on the MPEG-SRD standard and implements some field of view quality-based adaptation. And we implement the cuts in what we call dynamic editing. So our editing, our snap changes are dynamic in the sense that they do not require any modification of the video file. And they are only enacted at the time of the playback. So we describe the different cuts over the videos into an XML file, so specifying, of course, the time that the cut has to happen, and the angular sector to which the field of view must be repositioned, and the overlapping tiles that are involved in this field of view, so as to download them in priority in high quality. And the player just has to download this additional XML file at the beginning of the playback. So we also, of course, incorporated the knowledge of these cuts into our streaming logic. So specifically, the buffering process is not made only based on the current field of view anymore, but also uses the knowledge of the future cuts, so as to download more accurately the tiles in high quality. And as our streaming logic also implements a replacement for responsiveness of the system to the changes of the user's motion, what we do is that when a cut is going to happen, we disable the replacements. And this way, we expect also some benefits from editing, from dynamic editing onto the streaming process. So let me now show you the main results that we have obtained. But first, let me just comment the graphs. So we have here some blue and some red bars. So these two colors correspond to two types of contents on which we have assessed our system. So the blue bars corresponds to an advertisement content. So it's a commercial, it's a virtual visit of a luxury hotel in Monaco. And the red bars corresponds to a storytelling content. So that is a fiction. It's a thriller miniseries named Invisible, which is available on the Samsung store. And here we are going to compare specifically what we call dynamic editing with static editing. So here and here. So that corresponds to static editing corresponds to the reference, where we have this alignment of region of interest at the transitions, at the scene transitions. And dynamic editing corresponds to additionally having the snap changes, the snap changes into the different scenes as needed. Okay, and what we observe is that indeed we observe a reduction of user's motion, of head motion angular speed of about 30% between, so 20 to 30% in case we have dynamic editing. So that was an important result. And we've also identified that this translates into significant bandwidth savings up to 24%. We've also assessed some subjective metrics. So we've asked the users whether they could somehow detect some undesired rotations and if that bothered us. And what we identify is that most of the users did not detect any rotation, anything abnormal in the video, let's say, and in case they did, they were not bothered by it. And the last thing that we evaluated is how much snap changes helped the user into better understanding the goal of the content. So, for example, for the commercial, we asked the users whether they could identify some specific items that we wanted the users to remember, to see and to remember. And like, for example, in the virtual visit, that was like jacuzzi and stuff like that. And we could see that in the case we have snap changes onto the desired region of interest, that really helps the user to see and remember what the director intends to. And the same for the narrative content, where we made snap changes onto key events that the user were not has to not missed in order to understand the story plot. And here the same, it helped a lot. Okay, so that was our first lever that we have introduced to show that we can indeed design attention-driving techniques that can help on both aspects, on the networking aspect and on the user's experience aspect. So let me now talk about the second type of representative lever that we have introduced, and which is less based on editing and more based on interaction techniques with virtual environment. So the idea, the mindset that we have is still the same. We posit that the visual quality is not the only and not necessarily the best dimension in which the content, the VR content, can be impaired in order to fit into the available bandwidth. So we design a new type of impairment that we call virtual wall, and that consists in limiting the user's freedom, so limiting the user accessible angular sector in well-chosen periods. And here our hypothesis is that given for a given bandwidth budget, version of videos with virtual wall that enable a higher quality in the visual sector at the expense of less freedom can improve the user's quality of experience compared to legacy field of view-based adaptation based on linear compression and leaving the entire freedom. So we build here this technique onto recent knowledge that have been acquired on human attention in VR. So specifically, Sitzman and others in one showed that when presented with a new scene, a human first goes through an exploratory phase that can last up to 20 seconds. And in two, Almquist and others have made a taxonomy of the different types of scene that produce significantly different users' behavior. So specifically, they've identified 4 types of scenes: exploration, so where we do not really have some identifiable region of interest; rides with camera motion; static focus and moving focus, where the region of interest is either static or moving. So these are 4 types of scene. And then the question that we've asked is it possible to, given these specific features of the human attention in VR, to appropriately restrict the accessible angular sector in order to preserve the visual quality? So the idea here is, given these elements, can we restrict the angular sector in some periods of the video, so as to not send part of the sphere, saving the data in order to increase the quality in the visible sector? So what we did is that we designed such impairment as a subtle impairment of the user's experience with the virtual environment. And what we did is that we consider that this impairment is meant to be triggered only if the bandwidth drop happens in scenes where we have passed the exploration phase of the user and we are either in static focus or right scene. So the idea is that we are going, when the virtual wall here in red is triggered, we are going to prevent the user from accessing an entire angular sector of the sphere. So here the example is with a 180-degree split of the sphere, but that can be any angular split. And here what we are going to do is that when the longitude of the user's position reaches the virtual wall, then we are going to stop refreshing the field of view in longitude, but still refreshing it in latitude so that the user can keep their balance. So the video is going to show that. So here we have the video playing. Then we are going to reposition with a snap the user in front of the visible sector here. And if the user exceeds the visible sector, then we do not refresh the field of view anymore in longitude, but only in latitude. And then when they go back into the visible sector, they don't feel anything else. So the idea, the main idea here is that we wanted this degradation to be subtle in the sense that when reaching this limit here, the user can intuitively and quickly understand that they have to go back in the visible sector. So we, of course, implemented this technique into our app, and we formulated some hypotheses to test with user experience. So the first hypothesis that we formulated is that if the virtual wall is positioned after the exploration phase in scenes with concentrated saliency, that is static focus or right scenes, then a substantial fraction of users will seldom perceive this virtual wall. So that's the first hypothesis. And so basically the user are very unlikely to even go beyond the virtual wall. And if they go, then they might not go very often and go back very quickly to the visible sector. And the second hypothesis that we made is that compared with a reference with no virtual wall consuming the same amount of data, users may prefer the version with virtual wall, where the visual quality is higher in the visible sector, even though their freedom is a bit impaired. The idea being that, of course, they might not even feel this impairment given the location of the region of interest. So we considered a double stimulus approach to test this hypothesis with 18 users, assessing two versions of each video, one with and one without the virtual wall. We have considered two types of scenes, ride and static focus, with a total of 5 scenes. And all the virtual wall periods are positioned well after the first, the initial exploration phase. And we have set the encoding rate of each version based on the phase where the virtual wall is supposed to be used. So when we have a bandwidth drop, that happens in the focus phase. So here we considered that the bandwidth drop is by half. So the video rate is going to be cut in half. In case we have the whole sphere to be sent, so in case we do not have a virtual wall in the reference, we go from 10 to 5 megabits per second encoding. And in case we have a virtual wall, we can keep to 10 megabits per second encoding, as we are going to send only half of the sphere. And what we observed in the user experiments is that indeed, more than 50% of the users do not hit a virtual wall more than twice. And this fraction goes up to 88% in rides. So here for rides, we have a very low fraction of users that hit the wall several times. And that fraction is a bit higher, but not too high in the static scene. So that means that our hypothesis is confirmed, that the users indeed, as expected, rarely sense the virtual wall, even more so in high camera motion rides. And we next looked, of course, at the preference that they gave as to whether they preferred the version with higher visual quality and the virtual wall, or with no virtual wall and lower visual quality. For, of course, the same total data rate consumed. And here what we have found is that in the static scene, in the static focus scene, 68% of the users preferred the version with virtual wall, and 58% of the users in the right. So here the results do not allow to formally conclude onto our hypothesis. However, that was a first attempt, and what's very interesting is to make an analysis of the different elements, of the different components of the quality of experience that explain these amounts of preferences. So the first component of the quality of experience that we've assessed, that we've asked the users to grade, is the level of comfort. And very interestingly, the users did not rate their level of comfort lower in the virtual wall version than in the reference version. So that means that virtual wall is acceptable. The second component that we've looked at, of course, is the visual quality. That was one of our hypotheses. And here we could verify that indeed the preference is very much correlated with the grade of visual quality that the users gave. So here, the lower the visual quality assessed in the reference version, the higher, the more likely the users were to prefer the virtual wall version. So that was for the visual quality. And the last, the other component that we've asked the users to rate has been, of course, the responsiveness of the system to the head motion. And here, that has been very interesting because for the boxing scene, while the virtual wall is much longer on this scene, which explains also the higher fraction of hits in this scene, we can see that the responsiveness is only very loosely correlated with the preference given by the users. However, in the right scenes, even though the fraction of hits is very low, the number of hits is very low, the responsiveness is much correlated to the preference. So that gives us a hint that we may need to change, to modify, to improve the implementation of virtual wall, considering the camera motion in the scene. So, for example, that can be done by slowing down the playback of the scene so as to lower the amount of action, or dimming a bit the scene too. And the other thing that we could identify is when looking at the time of the hits, we could see that so the virtual walls were very long. Here in the y-axis, you have the seconds. So this is 10 seconds, this is 20 seconds. And very interestingly, we can see that before 10 seconds, there are a very, very few hits. And the second hit, mostly, if it is to happen, mostly happens above 10 seconds. So that also gives us a hint that we might better adapt to the user's attention by having the wall not last more than 10 seconds if possible, which already gives us some significant lever in the streaming algorithm. And to finish up on that, what we also did in this work is to assess not only the subjective metrics, as I've shown, but the application level metrics. The application level metrics are specifically the number of stalls, the number of playback interruptions, and the quality in the field of view. So here, let me explain what these figures are. So we compare the streaming algorithm incorporating the knowledge of the virtual wall with two references. so two streaming algorithms, which are the reference. So the first reference here is a streaming algorithm that is going to try as much as possible to keep the playback buffer full at the expense of not prioritizing a high quality in the field of view. And in the second reference algorithm, that's the contrary. So the algorithm is going to strive to have a high quality in the field of view at the expense of lowering the amount of buffered seconds. So here we have the following. In this period, I hope you can see my pointer. In this period, we consider that we have a bandwidth drop. And this is the period where we want to trigger the virtual wall in order to accommodate this bandwidth drop. So in this case of bandwidth drop, what we can see is that this conservative reference is indeed going to preserve the amount of buffer here in green at the expense of lowering the quality here in blue in the field of view, displayed in the field of view. In the case of the aggressive reference, we can see that the quality in the field of view is better maintained, but this comes at the expense of the playback buffer that entails some stalls, some interruptions in the playback, which is of course much detrimental. And with the virtual wall version, well, we have the best of both metrics. So we do not have any stalls, and we have the maximum quality, which is displayed in the field of view at each point in time. So that shows also the interest compared to legacy field of view based adaptation. So here, this is an additional impairment. We have field of view based adaptation, and we add this new lever in order to give even more degree of freedom to the streaming logic. So that was these two levers, and let me now come to the conclusions with the next two slides. Okay, so in this talk, what I've done is that I've reviewed some work that show that it is possible to design users' attention driving techniques in order to help VR streaming. So that can be instrumented, that can give more levers and more degrees of freedom to the streaming adaptation logic, to the streaming algorithms, in order to improve the quality of experience of streamed 360-degree videos. And from a multimedia networking perspective, that clearly opens the path to defining a whole new set of degrees of freedom, of levers to be wielded in the optimization of streaming logics for VR streaming. From a cinematography perspective, now one might object that I've not talked about the artistic aspect. And even though I've not talked about it, we really tried to consider it. I forgot to mention, by the way, that the first design of the editing cuts, the snap changes I've presented, we've made it in collaboration with a film production company in Cannes. However, additionally to that, the very core of our observation is the following. We observe that in case we want to stream, to design content which can accommodate streaming over realistic networks, well, the network requirements are dependent on the user motion, which is in turn dependent on the VR content and its editing. And all these three elements make up for the final level of user experience. So this is why I really advocate for a more global approach to transmission decisions and content editing and content design and editing design in order to maybe approach them jointly, or at least partly jointly, in order to help to benefit the user experience, specifically in next generation headsets that will have increased resolution. So this opens up a wide set of research perspectives and collaboration. And finally, let me just mention that we can think about several such levers, but once such levers have been defined and have been designed, the next step is to modulate them over time in order to produce the best VR experience, the experience that can be the most fluid and the most smoothest experience. So the next question to answer is, how can we dynamically trigger these new levers in order to adapt online to the user motion and the user's reaction to these levers, to the network variations, and to the different types of scene during the work content, in the content. And I envision that, methods from machine learning and deep learning in particular will be really key in this dynamic decision making. And specifically frameworks from the realm of reinforcement and imitation learning will be also very important to have the user into the loop. And that is on this topic that in the next talk, Miguel will present our very first steps in this domain. So I finish with that, and I thank you very much for your attention, and I'll be much happy to take questions.
So thank you, Lucille, for the very nice talk. If you're in the Zoom room and you would like to ask a question, you can raise your hand right now. We have about 5 minutes for questions. So I'll start with a question. So a lot of your work, it seems there are some levers that you have designed that have been derived from actual film cinematography, which has the purpose of aesthetics and storytelling, and from which you draw inspiration. And so how do you identify the techniques that can simultaneously tell stories and account for aesthetics, as well as address network efficiency issues? And would you consider creating new metaphors or new levers that did not exist in film before for VR, as it is a new media?
Yeah, so the idea here is that we mostly do not start from the networking aspect, and rather start from the content aspect. So I must say that for the first technique that I have presented, that was designed quite early in the domain. So most of the works that I've presented in the review in the second part were not out when we designed this technique. So the idea was really to say, okay, the content without fast cutting seems a bit boring, and plus when we consider cinematic VR and we want to be seated, then we have some hard time wringing our necks so as to see all around. So the idea here was really to say, okay, can we have a technique that can help the user experience? And amongst the different techniques that we can think of or that are already out there, what's the one that, or what are those which will give us some leverage to incorporate into the streaming algorithm? So basically techniques that will allow us to know precisely, deterministically in advance what will be the field of view of the user. So that's really we rather start from the user level aspect, from the user experience, and then kind of identify the possible techniques. In the possible techniques, those that will give us some freedom from the networking perspective.
Great. Is there any questions from the Zoom? I can ask another one. So, do you think that in the future the bandwidth capacities would be sufficient to address issues of VR content streaming, or will attention-driven techniques always be necessary to adapt the content to account for these streaming issues?
Okay, so this is a question that we take a lot from people who are not from the networking community, and that's absolutely legitimate from given all that we hear about 5G, etc., and optic networks, etc. But the answer is no for several reasons. So no, the network won't be sufficient for several reasons. So the first one is that if we, everyone who has tried out some existing VR systems already could see some problems, and we know that in order to fool the human eye, the equivalent data rate that we would need, even with H.265 compression, would be 5 gigabits per second. So 5 gigabits per second for one connection cannot be widely considered as reasonable. But even though we consider less important data rates, there are several reasons here. The thing is that we can even think about very high bandwidth that for your network access. The problem is that your network access is not your internet connection. That means that we experiment that quite a lot during these lockdown times, when a lot of people, when we consider massive usage of content and of the internet, we have congestion, and the congestion does not happen in the last hop, and this is where the bottlenecks are upper in the network, and this is where the content is going to be slowed down, and the quality of experience is going to be impaired. And the second aspect, or the third aspect rather, is really that, well, we really must think about VR for everyone, I think. And even in Western countries, we are not so much well equipped with high bandwidth network accesses, but we know that half of the population still doesn't have easy access to the internet, and most of the population that doesn't have easy access to the internet has access to it or will have access to it through mobile networks. And mobile networks, specifically when they are going to be used heavily, won't be able to deliver the type of data rates that will be required for VR content. So we really need to work on really more efficient. Well, when I say more efficient, compression is very efficient. It's just that it's not sufficient already for the type of usage scenarios in realistic environments, for not only for what's written in the standards, but what we really experience in terms of actual bandwidth in different places of the world.
I see. Well, thank you very much. We are somewhat just on time to finish the session. And so there was a question in the chat. We will post that on Discord, and Lucy, if you can answer that question on Discord later on.
Just a question.
Yes.
Sorry, if I get questions, where should I read questions? In Slack, in Discord, and where should I answer?
So in Discord, there's a channel devoted to WICED where I will post one of the questions that was posed here on Zoom, and you can answer it there.
Okay, great.
Great. Okay, so thank you. Thank you very much again for your talk, and thanks everyone for being here, and see you next session.
So the next session begins at 11 a.m. French time, right? So maybe we can clarify that then.
Yes.
And there'll be a different link. Yes.
And so
the link will be different.
Yes, the YouTube stream, hopefully that will work normally for the next session. And if you have questions, the same, you can post